We'll do a whatever. Exam is on Wednesday. Right now, I've got about half of it done. So the general kind of review material, chairs, and then stereochemistry covers roughly 50% of the exam. The rest of it is going to end up being largely the substitution and elimination stuff. Okay, so be familiar with that, be kind of aware of that. As soon as I get it completely put together, which should be sometime tomorrow, I'll post an announcement giving you more of a direct point breakdown on what's happening with each of it, or with each rough section. But I think right now it's 40 points worth of stereochemistry, and then 10 to 15 on chairs, and then maybe another 10 points worth on kind of general acid-based stuff. Okay? So what we'll do today is kind of talk about some things to just kind of fix a few issues. Go over elimination reactions again, because I've heard from several people that are having troubles with the elimination reactions. I don't blame you. Identifying the hydrogen when you're dealing with elimination reactions is not the easiest. Okay? It's pretty easy to lose track of that. So I'll go through it again and try and do it a little bit slower, see if we can get it nailed down. To start off with, I did make one slight adjustment on this slide, and it comes in with our meso compounds. Initially, I'd said just 2 chiral centers with meso compounds, and I have since changed my mind about that. Or rather, I found an exception to it being just 2 chiral centers. So if you come through a pairing of molecules and you think they're identical, evaluate one of those molecules. Okay? If they're identical, it doesn't matter which one you pick. Okay? Look to make sure it has at least 2 chiral centers. Okay? The next thing is going to be looking for an internal mirror plane. If it has both of those, then it's a meso compound. Okay? If it doesn't, then you're looking at just identical relationships. Okay? Does that kind of make sense? So let's pick a couple quick examples. If I looked at, let's do that one versus these 2 compounds. Okay, in red in the upper left. What would you expect? We go through the same molecular formula? Yep. Are they superimposable? Not immediately, okay, but we have sigma bonds. What's special about sigma bonds? We can freely rotate, so we can rotate the one on the right or left, depending on your preference, to the point where we end up finding out they are superimposable. So now we're at that identical rule, okay? And we've got to look for at least 2 chiral centers and a mirror plane, okay? We can start with either of those that we want to. I'm going to start with internal mirror plane. Do we have an internal mirror plane with this compound? Right through the middle. There is an internal mirror plane in this, okay, with either of those compounds. Okay? Do we have at least 2 chiral centers? No. Which means they're identical. Okay? Does that make sense? What happens if we now go to, let's try, as you may have already guessed, cyclopentanes happen to be a common theme. How about these 2 compounds? Same molecular formula. Yes, are they superimposable? Not directly. What do you have to do to superimpose them? Flip one of them and technically do a rotation, just because I ran out of space. Okay, which says we're now looking at that identical relationship. Okay, let's start with the internal mirror plane again. Do we have an internal mirror plane? Yeah. Yes. shoot, my internal mirror plane just had a little bend in it, but that's okay. We've got our internal mirror plane. Do we have at least 2 chiral centers?
Yes.
Yes. So what's the relationship between these two? These are meso. Okay? Kind of makes sense? Okay. So I'll leave that alone. Hopefully you guys are all super confident with that. Yeah? Super. As super as you can be, I guess. Elimination reactions. Okay? So these are a lot trickier to deal with. Okay? They're a derivative of our substitution reactions. So what we're looking at is, again, an alkyl halide to start off with, except this time, instead of giving a nucleophile, I've said I don't have that. Okay? So in the case of the substitution reactions, our alkyl halide either leaves or is in the process of leaving, forming a positive charge on that carbon. Okay? So that carbon becomes electrophilic, and we could stabilize that by using a nucleophile, allowing the nucleophile electrons to come in and stabilize our positive. Okay? But if we don't have that nucleophile, I need some other source of electrons. Okay? And we can't look somewhere else in the solution, because what else is in the solution? If it was a source of electrons in the solution, it would be called a nucleophile. So I can't go there. I have to find electrons somewhere within the structure. Okay? And the way this problem is formatted, it's easier to see where those electrons might be coming from. Because what we can do is compare across the reaction and look at our products. And we look at our products, what else has changed? Not only did our leaving group leave, but what else happened? We formed a double bond, and okay, we also had H plus formed. Okay? That H plus only had one source or one location. Where did that hydrogen come from? Okay, our other carbon. So we can highlight that in red here. Which is more electronegative, hydrogen or carbon? Carbon. So we would expect that the electrons stored up in that bond go more towards the carbon than towards the hydrogen. And now we've taken the electrons in that bond, we've turned it into a double bond. Hydrogen doesn't have those electrons anymore, and we're left with just H plus floating around. Okay, at least in these circumstances. Okay, does that kind of make sense as far as seeing what's changing in each case? Okay, the rest of it is looking at those options, trying to decide between those what things can possibly occur and how those individual reactions occur. Okay, and I'll leave you to go back over those slides. Our first option ends up being the mechanism for an E1 elimination. The next one is an E2, and the last one is ultimately impossible or not really likely. Okay? So we end up with 2 possible mechanisms. You'll notice that these rules, if you go back and compare these possible options back to what we did for the substitution eliminations, you'll find out they're very, very similar. So what does that mean about the rules that applied for an SN1 reaction? What do they do to the E1? Also going to apply to the E1 elimination. Okay, so that they overlap fairly well. Okay, at least between the SN1 and the E1. The SN2 and the E2 get a little bit trickier, okay, which is both a good thing and a bad thing. Okay, so this is supposed to be a blank slide. So let's go ahead and try and look at an example. Okay. We'll pick cyclohexane. Try to do this right. Pick a bromine and put a methyl here. Okay. Next thing I'm going to do is add a strong base. One of the things that you're going to need for your exam is to have a quick example for each of these possible reaction types. So if I ask you for a good Bronsted acid, you should say any good strong acid. So hydrochloric acid tends to be a common one. Okay? You need to have an example reagent handy because you'll need that to be able to process a lot of these problems. So if I say a good strong base, what would I expect to see for my base? Okay, OH minus is a possibility. Okay, that's not really an organic compound, so what's another good option? You might see it written as OCH3 or OMe. Okay? These ones are a little bit more common just because they're organic, whatever that says. Okay? The OH minus works as a decent base. It just has other complications, which we can also talk about. Okay? So, if we've got a strong base, that's ultimately the same thing as a strong nucleophile. Which mechanism is going to push with a strong nucleophile / base? Which type? One type or two type? It's going to be our two type reactions. If we have a strong nucleophile or strong base, we would expect the bimolecular reaction. It's so reactive, it's going to be involved in our rate limiting step. Okay? So, what we're saying is that that species needs to somehow come in and pull off a hydrogen at the same time as our leaving group leaves. Okay? So there's our leaving group taking the electrons, and we now have to somehow come up with some electron source to stabilize that partial positive carbon. Okay? And I've told you this is an elimination, so you don't need to worry about doing a substitution reaction. Okay? So in the elimination, what am I going to produce as my product? I need to have a double bond. What are the possible products? I think I know what you're saying. We get a possibility there. Oops, that was a bit sloppy. Or we could get the one vertical. That's a nice description. Or the one there. Okay? So we're trying to find an electron source for our partially positive carbon. Go ahead and try and highlight that carbon in green here. Okay? So what we're doing is now going to track that across to our products. Okay? How did we stabilize that positive carbon? What did we do? Okay, that is the full answer, giving it electrons from hydrogen, but I want to make it even easier than that. What was the net result? Where did those electrons end up? In the pi bond. So we ended up shifting and making a pi bond to stabilize that partially positive carbon. Okay, that was our goal here. Okay? So now we've got to come up with some way to form this pi bond. So let's evaluate the things that changed around it. Where's the orange carbon in my starting material? Right there. What things changed? How many bonds are in the product? How many bonds are shown to the orange carbon? 4 bonds. Of those 4, how many are hydrogen?
0.
In the product? 0. Okay, how about we move to the reactant? How many bonds are shown? 3 bonds, which means we must have an implied hydrogen. So we could go in and show that implied hydrogen. Why is it dashed? Because the CH3 is wedged. Okay? So there's that implied hydrogen. If we look at that orange carbon, what changed to go from reactant to product? That hydrogen disappeared. Okay? And it had to be picked up by something. Okay? In the formation of our product, we took those electrons and we put them into the pi bond. Okay? So if we take the orange electrons away from the hydrogen, what charge does the hydrogen become? Positive. What do I need to stabilize that positive? Electrons. Where do I have electrons? In the strong base. Okay, so we can show that base sharing electrons with the hydrogen. Hydrogen now has how many bonds? 2 bonds. Can hydrogen have 2 bonds? No. What do I have to do? Break a bond. I will take those electrons away and form the double bond. So I'm going to take the electrons from my hydrogen-carbon bond and put them into the pi bond. Okay? Questions? Yes, and then yes.
On the BR, there'd also be a hydrogen, right? Yeah.
Yes.
And then, so that has 1 hydrogen versus CH3, which has more hydrogens. How come it's not the 4 hydrogen? Does that make any sense? Why doesn't?
Why do we not look at the CH3?
Oh, why do we look at that hydrogen instead of the hydrogen over here? Why is it the orange instead of the green?
So let's take a look at the green one. Okay? Can we move those electrons in to stabilize that positive carbon? So that one's a lot trickier to evaluate. Okay? That's going to involve probably going back to the slides where I've got pictures of p orbitals and all sorts of fun overlap like that. That bond, our green hydrogen-carbon bond, is in a perpendicular orbital to the leaving of that. Okay? Those electrons cannot possibly come in to form a pi bond or to stabilize that carbon. Okay? So let's draw that real quickly and let's see if we can evaluate that a little bit better. So let's say we do take those electrons. Where are those electrons going to go? Where should you put them? We take the green electrons. Okay, I'm hearing a lot of people saying pi bond. Okay, so let's try and put it into the pi bond. How many bonds does our orange carbon now have? That's 5 bonds. So we can't put it into the pi bond. Not a bad thought, but that didn't work, so let's try again. Maybe we don't put them into the pi bond, because ultimately, the only reason we were getting electrons, that was really slow to stepwise it, okay, was to stabilize the partial positive carbon. Why form the pi bond if we can just move those electrons to the carbon? So let's go ahead and try and do that. What's the results of this structure? How many bonds does that carbon have? This one's tricky. We got rid of the carbon-hydrogen bond, so that's no longer there. What about the bromine? Also got rid of that one. So how many bonds does our carbon now have? 2. And a lone pair of electrons. This is a really goofy structure. Okay? It does exist in some cases, but it's extremely reactive. It's not only got a negative or the lone pair, but it also has an empty p orbital. Okay? The electrons, that lone pair, are in, again, perpendicular orbitals to where our leaving group left. The electrons can't be used to stabilize that positive charge. Okay? What we've formed here is technically a carbene, highly, highly reactive, very interesting chemistry. We aren't going to worry about those. Okay? So when people ask, why do we have to worry about orbitals? This is one of the reasons why you have to worry about orbitals, which is also why we... Okay? So are you happy that that green hydrogen doesn't work? Okay? So we've got the orange hydrogen generating our double bond. Do we have another hydrogen nearby? Why not the blue hydrogens? I know they don't show up very blue right now. Why not our methyl? It's not necessarily a bad thing or a good thing that it's not part of the ring. Why do I not pick the hydrogens out here? Positive charge, right? Generated on that bromine. I want to stabilize that as fast as possible. So what electron source should I try and get? Something close or something far? Close. How close are the hydrogens on our black methyl? We're looking at 1, 2, 3 bonds away. It's a bit of a stretch. Okay? We would have to move those electrons through a lot of intermediate atoms before we could actually get them over to stabilize the carbocation. Okay? So that's not going to be a really good option in this case. So the last option that we could go ahead and do, the reason I want to talk about that is because I wanted to draw blue hydrogens. So we could go through and take a look at the blue hydrogens as being an option. Okay, so what we could do is take the electrons away from one of those hydrogens, form the double bond there. Okay, so if we take a look at our blue carbon, how many bonds are shown to the blue carbon in the product? 3, which means there is 1 implied hydrogen. We go back to the reactant. I already showed you the answer there. How many hydrogens are on that blue carbon? 2. So what happened? We lost the hydrogen from that position. Okay? How could we help that hydrogen get pulled off? We could have our strong base come in, share electrons with the hydrogen, and push the electrons around. So 2 possible ways we could produce a product. Okay? Of these 2, which one would we prefer to form? So is there a difference between our products? Okay? Yeah. What's that difference? I don't quite want to look at that yet. And I didn't hear what everybody else said. What did everybody else say? It's where our double bond is located. Okay? Your answer is technically more correct, but this is easier. Okay? So what we want to do is look at those 2 structures and decide which of those is more reactive. Okay? If it's more reactive, what does that mean about the likelihood of it forming? Less likely, because it's not as stable. We always want to try and form the most stable product every single time. Okay? So the double bond is what makes each of these reactive. The double bond to react, we have to take those electrons and somehow push them out of the structure. Okay? So we could try and push the electrons out that direction, and it has to pass by a hydrogen. What if we tried to go that direction? It has to pass a CH3. What's the difference between a CH3 versus a hydrogen? CH3 is bigger, which ultimately means, in electron speak, it has more electrons. What does that mean about the likelihood of our double bond passing by that methyl group? Not very good. So really in that first case, in our orange double bond, we only have 1 site for possible reactivity, or 1 direction for reactivity. What happens when we move to our blue double bond? Well, there we go. There's 1 site. What's up here? In fact, we can even be color specific. We have a green hydrogen, which means what? We ultimately get 2 sites for potential reactivity. What does that mean about the reactivity? It's higher for our bottom one, which means what about the likelihood of it being the product? Less likely. Okay? So that one, make sure I did that right. Yes. Straightforward. Okay? That one's a straightforward one, I know. Okay? You have to evaluate how do we stabilize. I'm telling you it's an elimination reaction in this case. Okay, so we don't have to be concerned necessarily about what reaction we're running. We're just telling you straight up it's an elimination. Do it. Okay? Does that kind of make sense? Yes. This would be, now if we try to decide which mechanism would this one be? E2, why? Okay, we had a couple things going on here. Number 1, we're looking at this being a strong base. Strong base suggests which mechanism? Are 2 types. We formed a double bond, which means we're looking at an elimination. What else could be a red flag that we did this as an E2 mechanism? What was that? Everything happened in 1 step. Okay, in this case, I got a billion different things happening in 1 step, but each color happened technically in 1 step. Okay, so the way it's drawn up here is definitely in an E2 format. Okay, other questions on this one? Okay, I'm going to erase it, but end up drawing almost everything right back. What happens if this is our, I prefer O-methyl as a strong base, so that's what I'm going to use. If this is our reaction. What changed about the starting material? A lot? Little? Ultimately, the only thing that changed was Chapter 6, stereochemistry. Okay. What possible products would we expect out of this? It's a big hint. We just did it. We would accept the same two possible products. Okay, this is why this one's tricky. Okay. Everything we've just discussed would suggest which is our major product. Our first one, but ends up not forming. Okay. This is why I said this one was tricky. What mechanism did we move by? What type of reaction do you think this is? Elimination or substitution?
Elimination.
Why is it elimination?
Double bonds.
Okay, double bond. Or 1 or 2 type? 2, why?
Strong base.
Strong base. When we're moving in an E2 elimination or even the SN2, a lot of it comes down to sterics. Okay? And the big catchphrase that we put on the SN2 reactions was what? Come on, catchphrase. We're looking at backside attack. Close enough, right? It's not a sensitive mic. That's a good thing. Okay. We're looking at backside attack. Okay. So for an E2 elimination, we end up doing a very similar elimination. Okay. To our SN2. Our hydrogen source or our electron source must come from the backside of the leaving group leaving. Okay. Well, where's our leaving group leaving from? From the front. Okay, it's coming out at you, which means our electron source, our hydrogen, must be removed from the back. Okay, so we'll go back through and look at our possible hydrogens. Where's the hydrogen on now our red carbon? It's coming out at you. How do you know it's coming out at you? Because the CH3 is going away. How about, let's go wild. Let's make it purple. How about our purple hydrogens? One's for sure coming at you. Where's the other one? For sure going away. So when we go through and look at our elimination now, because it's an E2 elimination and because I must do the backside attack, okay, the hydrogen must be removed from the back side. Which hydrogen is on the back side of that leaving group leaving? Our purple dashed. Which means, where does our double bond form? Right there, and we end up with our double bond forming in the least substituted position. Okay? So when it comes to E2 eliminations, they're much trickier because you must have that alignment. It's how this reaction works. If you don't have that alignment, then the elimination doesn't occur. What if I'd started with, ooh, this is a good question. I like this question. What if this was my starting material? Oh, I'm going to make it even trickier. Heck yeah. There we go. Boom. Dangerous. I'm going to make this extra hard. Substitution or elimination. I'm going to give you the complete option. You can do whichever one works. Okay. If it's an elimination, what do we have to get rid of? What else should we draw on our structure if we think it's going to be an elimination? We need to draw in our hydrogens. Okay, we need to move to the next atom over. There's one hydrogen being wedged, right? We move to the other position. Hydrogen wedged. Do we have a hydrogen that is the opposite of our leaving group? No. Can the elimination reaction occur? No.
Does that go back to the primary, secondary?
No. This goes back solely to making sure your hydrogen, your leaving group, and your hydrogens are in anti-alignment. So it's strictly just based on the elimination. Okay. Now the trick, can we do a substitution reaction? Okay, what mechanism would it have to go by? Okay, how do we decide between 1 and 2? What do we need to do? Strong base or strong nucleophile. We won't worry about it being a base anymore. Why not? Because it can't be the elimination reaction, which means we're now looking at this species acting as a nucleophile. Is that a strong or weak nucleophile? Strong nucleophile because it is negatively charged. So strong nucleophile means which mechanism? SN2. We take a look at our substrate. Is our substrate, how would we classify that? Where our leaving group is? Primary, secondary, tertiary? Take a look at that carbon. How many carbons are attached to it? 2, which means, can I do an elimination, or sorry, a substitution with a secondary? Yes. What's the product? So we can be tentative at first. Let's just draw in those methyls. What would I expect at my green carbon? What should be there now? Should be O methyl. There's partial credit. Okay? Final credit, what do you need to add? No, I wouldn't care about the bromide. Why do I not care about the bromide? It's not organic. I don't care. I started with stereochemistry in the reactant, which means you've got to end with it. Okay? So now we've got to be careful with applying this. What happened with our methyls? Okay, our dashed methyls. Did we do anything to them? No. So what should we do in our product? We should leave them the same. Minimize as much as possible any changes until the last second. Okay, if you've got to change something later, then go ahead and do it, but try and prevent those changes first. Where did the O-methyl come in from? It had to come in from the backside, which would mean, what would I show in the product? Has to be dashed. Yes.
For example, where you have the or whatever, it doesn't have the wedge or dash, so why doesn't that one have it?
Oh, good call. I should have specified it on that one. I didn't because the first one doesn't need it because it's sp2. That should absolutely be dashed. Good call. And then why do we not need the dash in the other case here? What's the hybridization of that center carbon? sp2, trigonal planar, no need to show wedges and dashes. Okay? I wouldn't take off points for it. I'd circle it, maybe make an angry face so you didn't do it again, or pretend to take off points. I do that too. Okay? I write -5 and then don't take it out when I total it. Yes?
Well, so for the bottom one, you have a hydrogen coming away. So does that not affect how the base comes in for the substitution?
The nucleophile comes in for the substitution.
Right.
As you do that, you get an inversion of stereochemistry about that point.
Just about that point?
Yep, just about that point. Okay? Just to make it really fun, what ifs, everybody loves what ifs, right? Let's add that. Okay, I know, okay, fine. Let me erase everything, I'll draw it again. Okay. What if that was my starting material? Everybody agree with that? Don't. Everybody agree with that? No, why not? Classify that alkyl halide for me. What is it? It's tertiary. If it's tertiary, do we see the SN2? No. So we could push a no reaction. The adding of that methyl actually makes things a little bit more complicated because what else do we add out there? It's not just a carbon, but we also put a hydrogen that's now close enough to do an elimination. Okay, so in that case, we would probably, I actually wanted no reaction in that. I didn't actually see that until after I drew it. What we would probably get would be that for a product. Okay.
Can you show one that would have no reaction? Or just know that?
I can, with these structures, no, but I can show a no reaction here real quickly. Okay, I've got a strong nucleophile, which means what type of reaction? We're looking at a 2 type. That could be a nucleophile or a base, so we can't decide based on that species alone if it's elimination or substitution. Now we'd move to our substrate. What kind of substrate do we have? Primary, secondary, tertiary? Our primary, secondary, tertiary only works on sp3 type carbons. What's the hybridization of that carbon? sp2. We classify that based on its hybridization. It's an sp2 carbon. What's the reactivity of sp2 carbons in substitution, or even for that matter, elimination reactions? It's a lot lower. Okay, so we absolutely won't see the substitution reaction here. The elimination is a little bit trickier. That's probably not a strong enough base to form the internal triple bond. We probably wouldn't be able to do that with a strong base. Okay, so that would be one that I would classify, as far as you guys are concerned, as a no reaction. Okay, questions about that? I know, easy, right? Okay, so I really did intend for you guys to actually work on the quiz and ask other questions. So let me just kind of push through some of these reviews. So we started this off with looking at the elimination reactions. So ultimately, when you go through and answer any question, you should be asking yourself all of these as questions. What does the substrate tell you? What does the base or nucleophile in a second tell you? What does the leaving group tell you? Leaving group doesn't tell you anything. That one's pretty useless to look at least at this point, because we're looking at alkyl halides or no reactions. So the leaving group isn't important yet. Substrate patterns. So if you don't like memorizing or remembering that an E2 product is always a stable product, you might memorize the substrate pattern. We look for tertiary, secondary, primary methyl groups. Okay? That's an interesting difference from our SN2, because in the SN2, what did we get? Reverse order. Okay? Why does it change? Because our primary concern in the elimination is making that stable product. We form a more stable product with a tertiary alkyl halide than we do with a zero area or primary. Okay? When we move to E1, we'll see our tertiary and secondary. One nice thing about the E1 is everything in this column is the same as everything in the SN1 column. Okay, so that's kind of nice. Solvent. Okay, did I tell you something about the solvent? Okay, the solvent will typically get written below an arrow. I think I mentioned that in the lecture slides posted. So we would see, didn't really leave myself any space, so we could say reagent or starting material. The other option, we could see a reagent up here, solvent, and then product. It's kind of our overall representation of where individual pieces might show up in a reaction. Okay, so the solvent's not important for the E2. For the E1, we expect polar protic solvents. Why do we expect polar protic solvents? Okay, that's the hard answer. It stabilizes the carbocation intermediate. The easy answer, it's the same as SN1. SN1 wanted a polar protic solvent. So it's a nice easy way to dodge the question. Okay, stereochemistry. When it comes to the E2, you must have that anti-orientation. Okay? Your leaving group and your hydrogen must be in the anti or opposite positions. Okay? It's not the easiest thing to see. Where is it easy to see? In a Newman projection. So what could you do? Draw the Newman projection. Okay, you'll notice I didn't do it for the chair. Any ideas why not? Because it's really hard. Okay? You can end up with cis or trans products with the E2, and that's because of this anti-orientation. Okay? When you get to the E1, you almost always see the trans. Why would we see the trans over the cis? What's that?
So then the electron groups are
Farther apart, which ultimately goes back to stability. Okay? We're always trying to form the most stable double bond. So that's Zaitsev's rule. Okay? So that's where we get our Zaitsev's products. That's regiochemistry. That's just deciding where the double bond goes. Okay? And I intentionally didn't talk about Hoffman, but if you take more advanced classes, you might see it. Okay? Please still work. Okay? So this is kind of the sequence of questions that I would expect you to kind of be asking yourself each time. So what I did was kind of broke them down into individual parts. Okay? So we can look at the strength of the nucleophile. Really, that should say nucleophile slash base. Why are the nucleophile and the base typically inseparable? What's the definition of a base? It's a proton acceptor. If it's going to accept protons, what charge does it need to be? Negatively charged. If we take a look at a nucleophile, okay, it's an electron donor, which means what charge is it typically? Negatively charged. What's the difference between a nucleophile and a base? There really isn't one. Okay? So we can look for the biggest difference, and that comes down to size. So when we look at a nucleophile, they're typically very small. Okay? The smaller our nucleophile, the better they act. Okay? Why would that make sense? They're trying to get in to react with a carbon. Okay? Where's the carbon in a structure? Usually buried behind everything, but hydrogens being our foremost issue. Okay? So to get into that carbon, it needs to be relatively small. When we look at the base, what's the issue with the base? It only needs to react with a hydrogen. Well, where are the hydrogens? On the outside of the structure. Easily accessible. I don't care about the size of the base. Okay? So it could be small or it could be big. Really our only difference between these is our nucleophile wants to be as small as possible. Okay? There's very few cases where you get strictly one versus the other. Your nucleophiles, halogens or halides, are strictly nucleophiles. Why are they not good bases? What happens if that acts as a base? What does it make? HI, HBr, HCl. What's special about those compounds? They're all strong acids, by definition, completely dissociated. So they won't act as bases. Your typical bases, the examples I gave here, pretty much the only one you need to be concerned about is the T-butoxide. Pretty sure I showed a structure of that in one of the other slides. You're looking at the T-butyl group with a negative oxygen attached. Okay? The other ones we'll talk about when we start talking about chapter 10, which we won't do a whole lot, but we'll do that after the exam. Some point after the exam. Okay? Oh, that's right. It's not talking. Okay? So we can look for the strength of the nucleophile to determine what order. Are we looking at either a 1 or a 2 type? If it's strong, we're looking at the 2 type. Okay? Bulky bases favor elimination. Why bulky? Because they're bad nucleophiles. Okay? So if it's a bulky base, we typically see the elimination reaction. When we look at substrate structure, why is that not on the slide? It's weird. Primary alkyl halides are the only ones that really undergo SN2s. Okay? Or that's the only mechanism that they really react by. We can sometimes force an E2 elimination, but that's usually a secondary mechanism or a secondary result. Okay? The SN2 is much more common. For a secondary halide, okay, that I would personally call the SOL halide because every single one of your mechanisms is going to hold true for a secondary halide. You have to find some information somewhere else to help you decide which mechanism to run by. Okay? Your tertiary alkyl halides, okay, aren't much better, but you at least eliminate the SN2 as a possibility. Okay? So you end up with the SN1, the E1, or the E2. Okay? The last one that's cut off here, high temperatures typically favor elimination. Why would high temperatures favor elimination? We're trying to break a carbon-hydrogen bond. Okay? That's a nonpolar bond, not particularly easy or willing to break, regardless of the concentrations of anything else present. Okay? So we want to facilitate that as best as possible by adding enough heat to cause that bond to vibrate more such that it can break, so that we can increase the odds of that happening. It really just messed with all of this. This looks a lot better in the old slides. We've got rates listed on here. Again, just trying to summarize the individual pieces. Okay, what things that you can kind of expect under each reaction. That's unintelligible, so I'm going to say don't look at that. We're just going to move on. But it is much nicer looking in the actual slides that are posted. Okay, and these are just copied and pasted from that. Okay. The last one, which isn't quite as big of an issue, but I do want to mention it. We're looking at the complications of each of these reactions. So in an SN1 reaction, our big complication is that we lose stereochemistry. Okay? And by lose, we end up with a racemic mixture. Okay? So that's our SN1. Try and do color matching. And in SN1 reaction, we get racemic. The other big issue is that it's always going to run simultaneously to the E1. Okay? We can limit that a little bit. How do we limit that? What was bullet point 4 2 slides ago? Heat. So how can we limit the elimination reaction? don't heat it. Okay? When we move to the SN2 reaction, we get a lot more issues as far as our complications. That did not make it look nicer to read. SN2 reactions, we get an inversion of stereochemistry. So if you start with a stereocenter, it's going to swap. It's going to move from R to S. Okay? What's a big red flag that I'm asking you to tell me about the stereochemistry? How about if I drew this as a starting material? Do you think I'm asking about stereochemistry? Why not? I haven't specified the wedge and the dash. Okay? As soon as I put that wedge on, now you need to specify stereochemistry. It's something I'm fishing for and expecting to see in the product. If you aren't comfortable, do the reaction assuming there's no stereochemistry. Okay? Leave it as is until you're comfortable answering completely. At very least, you'll get partial credit because you did the correct reaction, say a substitution or an elimination. Okay? When we move to the elimination reactions, the E1, I don't know why I wrote these down here as complications for our E1. Not really complications. So the E1, I would say really the only complication is that we're looking at a simultaneous SN1 reaction. That's going to be the biggest issue. The rest of that is just kind of natural E1 results. The E2, as we've now seen a couple times, our biggest issue with our E2, we need to have that anti-alignment. Okay? If we've got that anti-arrangement of our leaving group and our hydrogen, we're good to go. Okay? Go through, draw the product. I think that's it. Yeah, that is it. So I'm going to go ahead and stop